Today we're talking about rational expressions. We've already talked about rational numbers. Let's remind ourselves the definition of what a rational number is. It's a number that can be written as a ratio, right? Rational ratio of A to B. But A and B, I don't mean an equal sign there. A and B are what kind of numbers? They're natural. Sorry, they're integers. Making all kinds of mistakes here. So A is an integer and B is an integer. Right? So loosely we'll say numbers that can be written as fractions, but not fractions like pi over 3 or the square root of 7 over 7. Numbers that can be written as fractions where each number can be written as a ratio. Maybe that ratio reduces to a whole number. Maybe it's already reduced, but that's a rational number. A rational expression is very similar. Rational expression is all functions, and we'll talk more about functions in the next chapter. All functions that can be written as a ratio of these things, where P and R are polynomials. So let's just look at a couple examples here. Here's a polynomial, right? Px squared, let's just do it in one variable. 3x squared minus 2x plus 1 over 5x to the 17th plus 6. Here's a polynomial. Here's a polynomial. This thing is a rational expression. No roots, no non-natural powers, just 0th power, 1st, 2nd, 3rd, 4th, etc. No trig functions, no variables as exponents. Basically what we'd expect, polynomial divided by polynomial. Well, it's important that we see the parallel between rational expressions and rational numbers, because everything that we're going to do with rational expressions is what we've been doing with rational numbers. So let's take a look at some rational numbers like 14 over 21. What do you think I would like you to do with that? Maybe reduce. So take a minute to do that. Okay. Hopefully you've noticed that you have 2 times 7 divided by 3 times 7. Cancel the 7s. And you get 2/3. could we reduce 14 over 21 as, let's say, 11 plus 3 and 11 plus 10. Is that true, first of all? 11 plus 3 is 14. 11 plus 10 is 21. So cancel the 11s. 3/10, right? Of course not. Canceling only works when we're dividing, multiplying, right? Times 7 divided by 7. The associative property of multiplication works here. That's not going to be the case here. Right? In order to cancel, we must factor. We must write our original expression as a product and cancel a number that appears as a factor on the top and the bottom. Why are we getting into that to such detail? Because we can reduce rational expressions that we've already seen before. Right? A monomial is really easy. So cancel the 7s, cancel the x's. I have 2 and x left up top, and 3 and y on the bottom. Very nice. Same idea with polynomials that are more than one term. So x squared minus x minus 6 over x squared minus 6x plus 9. Six and 9 have a common factor. Do we care? No. We need to factor the whole expression. We need to take this and take this. And if either of the factors up top are duplicated as factors on the bottom, then we can cancel. So let's review our factoring. X squared, that's going to be x times x. Negative 6, that could be 1 and 6. That gives me 6x and 1x. That's not going to work. Let's try again. How about 2 and 3? 2x and 3x. That sounds good, right? To get a negative 6, they have to have different signs. So I could say minus 2 plus 3. 3x minus 2x is 1x. I want negative 1. So it's got to be plus 2 and minus 3. That gives us 2x minus 3x is negative 1x. Boom. 2 times negative 3, negative 6. Boom. We're good. Down here, 9's a perfect square. X squared's a perfect square. I'm thinking we've got a perfect square trinomial here. Let's check. X times x is x squared. Plus 3x is 6x. Oh, I want minus 6x. So it's not 3 plus 3. It's got to be negative 3 and another negative 3. Now, if I was just factoring this, I might be tempted to write x minus 3 squared, and that's not wrong, but it makes it hard to cancel, right? Notice up here I had an x squared over x. It was easier to cancel that by literally writing it out and canceling. And we could say exponent rules 2 minus 1 is 1, so I have x to the first here. Exponent rules get harder to implement when we're dealing with binomial factors. Easier to just write it out, x minus 3, x minus 3. But we have all these x minus 3's, right? X plus 2 times this thing, then divided by this thing, That cancels out, leaving me just x plus 2 up top and just x minus 3 on the bottom. And that is our reduced rational expression. Same way we reduce more complicated monomials versus simply numeric monomials, but it's the same process. Not this process, right? That one was wrong. This process. Cancel the common factor of 7, cancel the common factor of 7x, cancel the common factor x minus 3.